First of all, I would like to thank Alex and Ivan for the organization of this meeting and for the invitations for this talk. My talk will be about something I've been thinking about for a long time, but which are not completely developed yet. Then I will put things more in terms of guesses or curiosities in order to submit you for criticisms and perhaps to get some feedback. Then let's see what I intend to mean. Oh, here. What? Can I change the page? Okay, can I? The first is the question already asked here in other talks. What are inconsistencies? According to the Oxford Dictionary, inconsistent is a noun that applies, for instance, in situations like A and B are inconsistent. That is, if something is inconsistent, we may ask, inconsistent with what? So inconsistency is inconsistent with something, at least it seems to be in intuitive account. Furthermore, for the sake of precision, inconsistent and consistency are words expressing syntactic notions, more in logical terms, that should be adequately used only in connection with formal systems. What I mean? I mean that in the scope of formal systems, we may find a way to express the notions of consistency and inconsistency. But generally speaking, in usual parlance or in science in general, it's quite difficult to classify something as inconsistent. We need to define or at least to characterize in some way these terms. Then, in the terms of a precise language, if L is a language of a theory T encompassing a symbol of negation, neg, and alpha is a formula, then you know that if from T we derive alpha and also derives the negation of alpha, then usual and in the most known systems you derive the conjunction of alpha and its negation. Thus, T is inconsistent or contradictory, yet here enters the word contradictory. Otherwise, T is consistent. Then here, in my exposition, I'm confunding inconsistency with contradictoriety. Yes, but perhaps some of you has already mentioned the necessity of distinguishing more or less the sense of mechanics in the morning. I think it's going to be quite interesting to distinguish, at least for science, between inconsistency and contradictories. But here I will take them as synonymous. Then you know that within classical logic, most known systems, if you have alpha and its negation, then you derive a beta, or beta being a form or whatever. Then you say that a contradiction entails everything, that's the explosion rule. But a consistent logic, as you know, were proposed to block this conclusion. We may have a contradictory formulas and even a contradiction without explosion in general. This is the usual way to think about. The great problem, according to my opinion, is to explain what is negation. That's, I think, is one of the most problematic things concerning paraconsistent logics and paraconsistent in general. What does the symbol of a negation means? We may say that with a paraconsistent logic, we may admit both alpha and its negation, but what do you mean by the negation? Can you say that a number is even and that it's not even? Of course, makes no sense. This is not a good contradiction, so to say. Can we say that a quantum entity is a particle and that it's a wave? Maybe some people say that, but here we need some care in order to classify a wave as being something which is not a particle and vice versa. Things are not so easy. Perhaps the better characterization of the intuitive idea of negation is given by the standard truth table of contradictory formulas. You know the formulas already, but of course this does not cover the negation of the predicate calculus, for instance. Typically, in this case of the predicated calculus, we need to test this notion of true in the standard logic. The square of position, mentioned already here today, also doesn't happen due to the limitation of syllogisms. And if you take, for instance, contradictors as the red line is here in the square of contradiction, okay, this is a way to see things. It's a model for a negation. But usually, syllogism is very limited. We don't have a theory of a relation, for instance. Then this is not a good solution, even for science. Okay, then in order to see what we can say about inconsistency, let's guess about a way of constructing a scientific theory. I suggest that we start with the interest in investigating a certain domain, R, which you call reality. Okay, we have a biologist has some ants or some fishes. Okay, the reality, something to be investigated. In general, we investigate in this domain for a certain P, that is a certain, I called it a phenomenology. Our account about the reality, our ideas, perhaps I can use in the sense I already mentioned here, thought experiments about the reality, something which gave me intuitions about the things I'm dealing with. This is, in my opinion, a metaphysical schema about R, the way we understand R. Of course, this can change from scientist to scientist. Each one has its own phenomenology, or perhaps different cultures have different phenomenologies in this sense, and so on. But starting with this phenomenology, it's an important observation. If you are not a realist, perhaps you can disconsider the part R, the part in yellow. You start with the phenomenology, saying that my reality is that the things I have as a phenomenology about the world or about something. My scheme is independent of such a supposition. You may be a realist assuming that R exists in certain circumstances, or it does not. You choose. But starting with such a phenomenology, you elaborate a PM. What is a PM? A phenomenological model or a pre-theory. In formal theory, we elaborate about R with basis in our phenomenology. That is an informal approach, an informal account to this reality. Okay, I said in the fourth item, you can start with phenomenology if you believe that the phenomenology we get is the reality. Okay, then we have three stages. The reality to be investigated, we have a certain phenomenology about this reality, and then analyzing these kind of things, we formulate a pre-theory, an informal theory, something you could refer to in terms of a mathematical model. I will give you examples. Okay. For instance, some examples of PMs, previous phenomenological models. Galileo's theory of the falling bodies. Galileo considered just some bodies which act as rocks or hammers and arrived experimentally, intuitively, to his famous equations. IH is equal half of GT squared. You know how, perhaps you have read or how Galileo is very brilliant man, how he got his equation by making experiments. Another example could be Darwin's theory of natural selection. They are informal theories. What do I mean by informal? Not formalized, not axiomatized. Informal state. Darwin's theory of natural selections. Observations gave him a phenomenology and an informal theory too. Fourier's heat equation, the famous equation of the heat transfer. Also from observations, guesses, intuitions, and imagination. And perhaps one of the most well-known examples, the infinitesimal calculus. It assumes a strong metaphysical encompassing infinitesimals. Then this is something I would like to emphasize. The link with the metaphysical hypothesis. I guess that we cannot do anything without the metaphysical suppositions. But this is a guess. Okay. Let's go further. Once we have the informal theory, the informal model, I have, for instance, Darwin's theory of natural selection, we can go further. Many philosophers wish to go further. Further in what direction? In the direction of the study of the theory itself. Then we formulate what I called here the theory, as I prefer to call the theory. That is an axiomatic version of our informal theory or a formalized version of our informal theory. This makes the theory which was previously already interpreted. It had already a certain informal semantics. Darwin spoke about the kinds of things, birds and so on. We had already a semantics. Now, in the theory T, we don't have any more semantics. It becomes an abstract entity and just a mathematical device. Then theory is the theory stricto sensu, axiomatic or formal. And as an abstract entity, such a theory may have models. Models in the sense of logic. That is, as I call the abstract models of T. Usually set theoretical structures if you are using a set theory in the mathematics. It's important to mention because this link between theory and models is very difficult because you cannot use it here first order model theory in general if the theory is a theory of science. For instance, general relativity, quantum mechanics, particle mechanics. Our books of model theory are not completely useful here because the theories usually must be axiomatized in higher order logics. And we don't have a model theory for higher order structures. We need to study case to case. Then we cannot generalize it, saying that we have a way to study these structures we call models. But then we have, from the informal theory, I construct, there are several different ways to do that. Anyone can do its own way of approach, a certain formal theory or axiomatic theory, and as an abstract entity, this theory will have infinitely many models in principle. Then you can choose one of them to represent the intended model. You ascribe to the elements of the model by, for instance, by coordinate rules, I don't know, interpretations in order to make it to cope with the reality, at least in our phenomenon, at least in our conception. Look at that, ignore that. It's mine, I think. I'm sorry. Okay, then you choose one of the models to be the intended model. You can do it, and there are lots of ways to do that. Then we may have also other models, like iconic models and so on. This is very well discussed in the literature. One of them is choosing to be the intended model, built to represent R according to our phenomenology. Important. This is an important thing. We cannot prove that the M fixes the reality. We need to assume that. This is interesting. This is more like in computer science, there is something called the Church's thesis. You know that. Church's thesis basically relates an informal notion of functions, how can I say? Standard functions you can make by hand, and recursive functions which has a very right mathematical definition. Then you relate something mathematically well defined and another thing which is informal. You cannot prove that they fit because one of them is completely intuitive. The same happens here. Reality is something we imagine, we suppose. Now we have a mathematical model. It's impossible to prove that they fit one another. We need to make a supposition. by means of experiments and so on, at least apparently the model we have is saving the phenomena, is being compatible with the experiments we do. And then we accept the theory and the models provisorily until another thing will happen and obligates us to change that. Then, the right choice of the model at least save the appearances. These are more empiricist view, but this is me. Well, where are the inconsistencies? That's the problem. Then I ask, can inconsistencies occur in the reality? In my humble opinion, no one knows. I, for instance, never saw a contradiction running in the garden. I don't know if you did, but I don't. I asked Graham Priest once, please show me a contradiction. Here Locke decided the liar, the sentence of the liar. No, I would like the contradiction in reality, in some sense of reality. I never saw a contradiction. I don't know if they exist. I suppose they don't. Then in the R part, I suspended the judgment. But what about the phenomenological part? Can be contradictions there? I guess that within our Western culture, it would be difficult to intuitively form a contradictory phenomenology. We don't do that, we here, because we are accustomed with our logic, our teachings, our classes, our way of reasoning, and for sure you will not form a contradictory Weltanschauung, if I can use this word. But if you are one of the people, the members of the Zand people is a tribe in Africa, which and they believe in contradictions, in true contradictions. But maybe if you are an Azande, then perhaps you form a phenomenology involving contradictions. But I don't believe that we here do that. But this is something indisputable. Then, in the P part, maybe. Perhaps you can say that the reality is hidden. Bernard España has a very, very interesting concept of the veiled reality, but the reality behind a certain veil. We cannot know it perfectly because it's hidden. I don't believe that, because this is just an epistemological problem. The reality is there. We epistemologically don't have access to it. Then the España's idea for me is not feasible in this sense. Then, but this is, the España's view, in my opinion, just an epistemological question. In our standard way of thinking, I believe, P, the phenomenological part, is supposed to be not contradictory. I don't believe that any one of you will analyze a certain field of knowledge and form a phenomenology involving contradictions. You'll be wrong, probably. But can the model, the phenomenological model, the informal theory be inconsistent? Of course, yes. We can elaborate an inconsistent informal theory. For instance, it was said before, Bohr's theory of the atom, according to some people, because this is disputable if it involves a really contradiction or not. The infinitesimal calculus, okay, this is more cogent example, would be examples of informal theories involving really contradictory things. Well, what about the other parts? Let me say that the phenomenological model then may be inconsistent, but this would be regarded as something to be overcome. It was explained before in the two talks here. There are lots of ways of trying to overcome the contradictions, or perhaps for dialecticists, perhaps to keep them. It depends on the philosophical creeds of the scientist. But I think that the phenomenological model is the land of proofs and refutations. I would like to advance here that I'm not defending Popper's fallibilism, no, but I agree with his idea in Lakatos concerning mathematics, concerning proofs and refutations. You try to prove, and if you got some refutations, some inconsistencies, you tend to, if you are not someone to accept the contradictions, you tend to revise your theory. And these people, Popper, Lakatos, and lots of others, offered ways to revise our theories due to these refutations. Well, but the scientist in general puts the innocent, the contradictions, which are not so important to him, between parentheses and continues to work until some not supplantable problem arrives. Others do not care about contradictions. I put here, I found Wittgenstein's remarks on the foundation of mathematics, but before today, Michaelis brought a very interesting quote, I completely forgot it, from Lakatos. I think it's more interesting, Lakatos' idea, that you keep it contradiction, if it is an innocent contradiction. But Wittgenstein has a very interesting remark here. He says, if a contradiction were not actually found in arithmetic, that would only prove that an arithmetic with such a contradiction could still render a very good service. That is, continue to work with contradictions. Okay, I mentioned here, yes, such arithmetics can be useful as a service, as a tool, but not for a fundamental mathematical theory. This should be analyzed further. You need to change logic here and so on. Then there are these stages where contradictions could appear according to my reflections not well developed. Look, inconsistency in the theory, in the axiomatic or in the formal theory. Now, once axiomatized with classical logic, it would be difficult to accept that T could be contradictory. Classical logic or standard logic, impressionistic logic, and so on. If a contradictory propositions are derived, of course the theory is wrong. If you are to accept the contradictory propositions, then of course you need to change logic. Priest's paraconsistent arithmetics is one of the examples. He developed a very interesting arithmetics grounded in his logic LP, already mentioned today. The first steps in a paraconsistent differential calculus were given by Italo Ottaviano and so many people, but they found very difficult to prove a problem until now, not overcome, I'm sure. But they developed a good part of differential calculus with a paraconsistent basis. But look at science, now science, scientific theories. Does anyone have seen a paraconsistent scientific theory? Do you know some? I don't know. No scientific theory grounded in a paraconsistent theory was, at least according to me, presented yet. I don't know. There are suppositions, how to do things, but no one presented a contradictory quantum mechanics or a contradictory physical theory. I don't know. Perhaps you know. I mean not a supposed inconsistent theory, but a real paraconsistent one that is grounded in a paraconsistent logic, either axiomatic or formal. Paraconsistent logics in this sense are used with technological applications, notwithstanding this. For instance, in robotics, expert systems in medicine, in law, in lots of applications, technological applications. But it was not used yet, according to me at least, maybe I'm wrong, to found science. This is just a supposition. Till now, I think there is no paraconsistent contradictions. But there is a way to approach a very nice contradictions in science by using a kind of paraconsistent logic called paraclassical logic. I will give you some idea about paracomplete logic, paraclassical logic, to those who doesn't know about them. Suppose that in T you derives alpha, and in T you derives beta, and from alpha you derives gamma, and from beta you derives the negation of gamma. Then we call such alpha and beta complementary. That is, complementary are two sentences, if you mean, so that from one of them you derive a sentence gamma, and from another one you derive the negation of gamma. Paraclassical logic avoids that the conjunction alpha and beta, from the conjunction of alpha and beta, you derive a contradiction. It's not an adjunctive logic. From alpha and beta, you cannot form in general its conjunction. Then, despite you derive gamma from alpha and not gamma from beta, you will not derive a contradiction because you cannot form the conjunction of alpha and gamma. This is the idea of complementarity. Why complementary proposition? Because it's motivated by Niels Bohr. Niels Bohr said, we need both, in the case of alpha and beta, to understand a certain phenomenon, but their conjunction leads to a contradiction. For instance, this example given, particle and wave aspects of a certain matter can be seen as complementary in this sense. That is, the particle aspect and the wave aspect. Matter has, in quantum mechanics, both aspects, but nothing is a particle in a wave at the same time. This is completely wrong. It depends on the experiments you do, the ways you prepare the experiments, you will behave something called a particle or as something called a wave. You need both to understand the phenomena, but they are not incompatible, they are complementary for the understanding of the phenomena. There is no contradiction in assuming both things, particles and waves, because both cases cannot appear together. This is true. Or you have a particle behavior or you have a wave behavior, not both. A quantum system, then, is never both a particle and a wave. And despite we don't know about its very nature. Then, paraphrasing the physiologist Dubois-Reymond, I think that in science in general, we still are in agreement with this maximum. Ignoramos et ignorabimus. We are ignorant and we shall remain ignorant. We don't know, and perhaps we will never know. We just guess. We form theories, we construct theories, experiment theories, and we live with the theories until we need to change them. We don't have right approaches to any field of knowledge. Well, then I will mention here an example, the cat, the famous Schrödinger cat. The cat and what is said in usual parlance, it's usual you will find in internet, in journals and so on. Scientists put one particle in two places at once. This is completely wrong. It's impossible because a particle, a quantum system, does not have a position. It has states, position states. It's a different thing. You need to speak about positions. When you speak then about the cat, this is a flexibility of language. You need to assume that we can speak of the cat, because really the theory speaks about the state of something we, in the interpretation, call a cat. But we speak of the states. The formalism of quantum mechanics speaks of states, observables, and probabilities. It doesn't speak of quantum systems, the formalism. But let's see, the Schrödinger cat. Then you know the history. There is a container completely closed, a cat inside, and a malignum experiment, said Schrödinger. There is a bottle with a poison and the radioactive material which can emit a radiation in, say, 1 hour. Or it emits a radiation or does not. If it emits the radiation, it makes some hammer act and break the bottle, and the poison arrives and kills the cat. If it does not emit the radiation, the cat continues alive. Then, after 1 hour, scientist goes to the container, opens the door, see the situation of the cat. There is no more quantum mechanics there. Now things became classical. Here you see the cat alive or the cat dead. But the question is, what happens before? What is the state of the cat before opening the door or before the measurement? Well, the state is the third possibility. The third possibility is a superposition of states. The cat is not alive and dead at the same time, as usually said. Completely wrong. You cannot say that. The cat is not alive and dead, because in order to be alive and dead, it needs to be in the two states at once, and it's not. The state is a superposition. It's a, look here, it's a vectorial sum. A vectorial sum, a sum of vectors in a Hilbert space, is not a logical conjunction. It's not A and B. It's A plus B, which is something completely different. Then, before the measurement, the state of the cat, in short, is this state. Psi is 1 over square of 2. This is not important because this coefficient, we take the square. The square is half. This is the probability. Then it has the half probability to be alive or the half probability to be dead. This is the state before measurement. When you open the door, this state, according to one of the fundamental postulates of quantum mechanics, collapses. This state disappears, and one of the forming states appear. That is, either the cat will be seen alive or you will be seen dead. Then the superposition collapses and is reduced to one of the states. The same for positions. If you have a screen with infinitely many possible positions for a particle to arrive there, what you have before the particle arrives? You have just a superposition of states. Each point in probability. When you make experiments, the point appears. Then you can measure the probability to arrive in such a point. Never in 2 points at once. Never. You have the probability to be here or the probability to be there. If after measurement you can have it here, you can find it here or there, but not what? Never. This is a misinterpretation. What can you explain that? It's easy to explain. Why this is not so? Because a negation in quantum mechanics is not classical negation. It's not the contradictoriness in the spherical position. It's contrariness in the top of the spherical position. The negation, the cat alive and cat dead are contraries. They can be both false. When they are both false? When the situation demands a third state. Which state? The superposition. Then you have here in blue, cat alive in a subspace of the relevant Hilbert space W. Its negation is here in the orthogonal complementation of W orthogonal. This is cat dead. But there are vectors which are not in one subspace, neither in another subspace. They are just the direct sum of the subspaces, and this is precisely the superposition. Then I emphasize here, the vector sum is not a logical conjunction. Alive plus dead is different from alive and dead. Alive and dead is not a quantum state. You cannot use it. So there is no contradiction here in the Kate or in the cat and so on. There are no contradictions. Here or in similar situations. For instance, a particle cannot be in 2 places at once. Then, in order to analyze inconsistencies in science, this is my guess, you need to carefully analyze the meaning of the notion of negation. When you say there are inconsistencies, what do you mean by that? You need to qualify. If you take it logically, purist, simple, you will deal with contradictory situations. In contradictory situations, strict classical logic, difficult you will apply in subjects such as quantum mechanics. Then, my conclusions. We need then to characterize what is an inconsistency. First, inconsistency is inconsistent with what? Perhaps we can say that something is inconsistent, a proposition is inconsistent. João Marcos has a very interesting logic when they have an operator, ball, in which the alpha ball says that alpha is inconsistent. This is a way of approaching very interesting para-consistent logic. You know who is here now, sure, you know this system, which is very interesting. Perhaps you can say that. But a proposition taken in isolation. In Priest's chosen sentence, I am not lying. I don't believe in Priest's example. But can an object be inconsistent? I don't know. I really don't know. I never saw one object, inconsistent object, I don't know. I cannot even imagine an object. What are the definitions of these things? These are important to define. You need to, as Voltaire said, can you discuss with me? Okay, then define your terms. If not, you cannot speak. You cannot even discuss. Concerning theories, if some theory negates another theory, then of course we need to revise the theory, grounded on classical logic. At least if you are a dialectist. Then you'll believe that alpha and not the alpha are about two, as Jonas explained. But if the negation is a para-consistent one, depending on our credos, we may accept it if you are para-consistent in some sense. But what is a para-consistent negation? I still don't know. In my opinion, no one knows. Every approach will give you some negation, you need to qualify. And there is no general negation, according to me, that applies to all fields and situations. Then you need to qualify. So, in order to avoid the ignoramus et ignorabimus, we need to agree with Hilbert, which was completely against the Bois-Reymond. Hilbert said, we wish to know and we will know. Then, in order to avoid this ignoramus et ignorabimus, perhaps we agree with Hilbert when he says that every definite mathematical problem must necessarily be susceptible of an exact settlement, either in the form of an actual answer to the question asked, or by the proof of the impossibility of its solution, and therefore the necessary failure of all attempts. But I'm not sure that that's possible to science, with science, perhaps with mathematics. Hilbert spoke about mathematics, not about science in general. As far as I know, I don't know if you, because he corrected me before. He said, oh, I said about task, he said, oh, but there is a situation where, I didn't remember the paper. Thank you, Alex. But perhaps this idea that we can superset the inconsistency, more or less what Hilbert is saying, we wish to know and you will know. I don't know if this applies to science. Perhaps in science we must to continue with the Bois-Reymond. Ignoramus et ignoramus. I don't know. This is something I submit to you. Thank you so much.